In this lecture, we will show that the reciprocal map R of z equals 1 over z, which we define over the extended complex plane, maps lines and circles onto lines and circles. Lines and circles are collectively referred to as clines, and so, according to the theorem, the reciprocal map maps clines onto clines. If z equals x plus y times I, where x and y are real, then 1 over z, which we set equal to z prime, equals x divided by x squared plus y squared minus y times I divided by x squared plus y squared. We define r of 0 to be infinity, and r of infinity to be 0. There is a transformation called the inversion map with respect to the unit circle that is similar to the reciprocal map. If z is non-zero and z star is the inversion of z with respect to the unit circle, then z star equals the conjugate of 1 over z, or the reciprocal of the conjugate of z. Z star is on the ray OZ, where O is the origin, and the product of the absolute values of z and z star equals 1. In another pair of videos, inversions of lines with respect to a circle and inversions of circles with respect to a circle, we showed that clines are mapped onto clines by the inversion map with respect to a circle. So for example, if z traces a path along a circle, z star will trace a cline. We are including the links to these videos in the description of this lecture. Z star and 1 over z are conjugates of each other, so that if z star traces a circle, 1 over z will trace a reflection of the circle that z star traces. The same will be true if z were to trace a path along a line. We can simply invoke the results of these two videos as proof of the main theorem in this exercise. In this lecture, however, we will mix in a bit of Cartesian coordinates to show directly that the reciprocal map R maps clines onto clines. We first prove the theorem when the reciprocal map is applied to lines. We consider line L, which we assume without loss of generality is vertical. If L were not to be vertical, we would then apply our rotation rho sub beta to make L a vertical line. Beta is the rotation angle of rho sub beta, and rho sub beta of z equals z times e raised to the power I times beta. The question is, how does first applying rho sub beta, then followed by the reciprocal map, affect the shape of the image of L under the reciprocal map? R of rho sub beta of z is 1 over rho sub beta of z, and this is equal to 1 divided by z times e raised to the power I times beta. And this is equal to e raised to the power minus I times beta divided by z, which is equal to e raised to the power minus I times beta times the reciprocal map applied to z. And so the image of a graph under the reciprocal map composed with rho sub beta is the rotation by the angle minus beta of the image of the graph produced by just the reciprocal map alone. And so we should get the same shape for the image under the reciprocal map whether or not it is composed with rho sub beta, so that without loss of generality we can assume that line L is a vertical line. First, we consider the case that line L is the imaginary axis, so that z equals y times I. If z is non-zero, 1 over z equals minus I over y, which is pure imaginary, so that 1 over z is still a point on the imaginary axis. R of 0 being infinity and R of infinity being 0 completes line L and its image under the reciprocal map. Therefore, the reciprocal map maps the imaginary axis onto itself. When line L is not the imaginary axis, z will be equal to h plus y times I, where h is non-zero and real, so that x equals h on line L. We can choose a rotation angle beta such that h ends up being positive, so that without loss of generality, we let h be greater than 0. Reversing these formulas, if z prime equals x prime plus y prime times I, where x prime and y prime are real numbers, then x should be equal to x prime divided by x prime squared plus y prime squared, and y should be equal to minus y prime divided by x prime squared plus y prime squared. Since x equals h on line L, h should be equal to x prime divided by x prime squared plus y prime squared. Or x prime squared plus y prime squared minus x prime divided by h is 0. We carry out completing the square. We divide this coefficient by 2 and add its square to the x terms, and to the right side of the equation. This part is equal to x prime minus 1 over 2h quantity squared. And we have the center radius form of the equation of a circle. We name this circle circle S. Its center is at 1 over 2h 0 and its radius is at 1 over 2h. To show that the reciprocal map is onto from line L to circle S, we parameterize circle S. If z prime is on circle S, we can write x prime parametrically as 1 over 2h times the quantity 1 plus cosine t, and y prime parametrically as 1 over 2h times sine t, where t is some real parameter. 1 over x prime plus y prime times I is equal to x prime minus y prime times I divided by x prime squared plus y prime squared. We cancel out one factor of 1 over 2h from the numerator and the denominator, and multiply out the rest of the denominator. Cosine squared plus sine squared is 1, so that this part is 2 plus 2 cosine t. This fraction simplifies to h, minus h times sine t divided by 1 plus cosine t times I, if cosine t is not equal to minus 1. So as long as cosine t is not equal to minus 1, a point on circle S must come from a point on the line x equals h or line L under the reciprocal map. And if cosine t equals minus 1, then sine t will be 0 so that both x prime and y prime are 0, so that z prime is 0. Now our inverse of 0 is infinity, and infinity is also on line L on the extended complex plane. Therefore, the reciprocal map is onto from line L into circle S. When the Cline is a circle which we call circle T, we apply the same idea of rotating the plane so that the center of the circle is on the real axis. Suppose that the center of circle T is at big H 0 on the non-negative real axis. First, we consider the case that the origin is on circle T so that big H is positive and the radius is equal to big H. This brings us back to the second case for the line when we had applied the reciprocal map to line L, whose equation was x equals little h. For that case, the reciprocal map mapped line L onto the circle S, whose center was at 1 divided by 2 small h 0, and whose radius was 1 divided by 2 small h. So we set big H and R both equal to 1 over 2 small h, so that circle T and circle S are one and the same circle. The inverse of the reciprocal map being itself, the inverse image of line L is the reciprocal map applied to L, which we had found earlier to be circle S, and circle S is also circle T. Therefore, the reciprocal map maps circle T onto line L. Now suppose this time that the origin is not on circle T, so that its radius little r is not equal to big H. If z is on circle T, then x minus h quantity squared plus y squared equals r squared. X is x prime divided by x prime squared plus y prime squared. And y is minus y prime divided by x prime squared plus y prime squared. We multiply this entire equation by x prime squared plus y prime squared quantity squared. We should get this equation after a little multiplication and some rearranging of the terms. X prime squared plus y prime squared is never 0 since z prime is 0 only if z is infinity, which can't happen on circle T, so we can divide by x prime squared plus y prime squared and rearrange the terms in the equation to get this next equation. R squared minus big H squared is non-zero since r is not equal to big H, and so we divide by r squared minus big H squared to get this next equation. And we carry out completing the square a second time. We divide this coefficient by 2 and add its square to both sides of the equation. This part is a perfect square. We simplify the right side to get r squared divided by r squared minus big H squared quantity squared. This is an equation of a circle that we call circle U and whose center is at minus big H divided by r squared minus big H squared 0 and whose radius is the absolute value of r divided by r squared minus big H squared. So the reciprocal map maps circle T into circle U, and we now explain why the reciprocal map is surjective from circle T onto circle U. All we have to do is reverse the steps that got us from circle T to circle U. Take any z prime or x prime plus y prime times I on circle U. Every z prime on circle U satisfies this equation. This equation is equivalent to this equation. This in turn is equivalent to this equation, which is equivalent to this other equation, which is equivalent to this equation in center radius form, where x equals x prime divided by x prime squared plus y prime squared, and y equals minus y prime divided by x prime squared plus y prime squared, and these give us the formulas for the point xy on circle T. And so for each point z prime on circle U, there is a corresponding point z on circle T where the reciprocal map applied to z is z prime. Therefore, the reciprocal map is surjective from circle T onto circle U.